Peng from CISPA, and Yun from NetApp. So what's the dataset distillation? In recent years, the ever-increasing scale of data significantly increases the cost of storage, training time, energy usage, and so on. Many researchers cannot afford such a cost in the real world. Therefore, dataset distillation is an emerging research direction to improve data efficiency when training DNN models. So from the figure on the right, the core idea is to distill a large dataset into a smaller dataset. And the goal is that a model trained on this distilled dataset can attain comparable performance to a model trained on the original training dataset. So for example, the scale of CIFAR-10 of the original training dataset, of CIFAR-10 is 50,000, with a performance of 84%. But we can achieve 64% of the test accuracy just by using 100 synthetic images from the dataset distillation. Owing to these advantages, we believe that dataset distillation will be offered as a service and play an important role in many machine learning applications in the future. However, dataset distillation is a mixed blessing. First, it's essentially a DNN model, which is vulnerable to security and privacy issues. From dataset distillation algorithm, which is the figure on the right, we should calculate the gradient from an upstream model by the distilled dataset and the original training dataset for updating the distilled images. As a result, there will be many security and privacy issues against these DNN models, such as backdoor attacks, membership inference, and previous works have argued about the privacy of dataset distillation. In addition, so from this figure on the right, humans cannot distinguish the distilled images just by their naked eyes. If I don't tell you what class it belongs to, nobody can recognize it. Actually, it's an airplane from class 0 of CIFAR-10. And they will allow the adversary to hide some information in these distilled images. So in this paper, we follow this concern and try to inject some triggers into the distilled images and poison the distilled dataset. However, based on our test, classic attacks cannot be directly applied to this distilled dataset. So the reason here are, first, distilled datasets are too small to launch such attacks. For example, when distilling 100 synthetic data of CIFAR-10 and 10 images of each class with the 0.01 poisoning ratio, the same as original backdoor attacks, we can only inject the trigger into one image. And based on our test, the attack performance is also bad. And second, a human inspection can quickly mitigate such attacks. So here comes our research questions. It's possible to inject trigger into a distilled dataset and launch backdoor attacks on the downstream models. And let me introduce the scenarios at first. So we envision the attacker as the malicious dataset distillation service provider. So two attack scenarios are taken into consideration in our study. The first is that the victim commissions the attacker to distill a specific dataset on their behalf. And this scenario is in line with the generic purpose of dataset distillation. And the second scenario is more on practical side. Instead of buying the original training dataset, the victim opts to purchase a smaller synthetic dataset from the service to reduce the cost. And based on previous questions and scenarios, we first think about if we could use a pre-trained trigger and add it into the original training dataset. And then we use this poison dataset for the distillation. So we propose our naive attack. The idea is simple. We add a pre-trained trigger, which is based on the badness, where the trigger is white pixel in the bottom right corner. and we use this dataset to distill a small synthetic dataset. However, this method is not as effective as we expect. In our test, for some dataset, we can achieve a good performance, but mostly not. So we try to go deeper. Can we optimize the trigger just based on the upstream models? Then we propose our protagonist, DOORPING. Different from naive attack, DOORPING needs to update the trigger at each epoch. Since the dataset distillation algorithm needs to update model parameters by the gradient of the original training dataset and the intermediate distilled dataset, we can update the trigger after model got updated, and then put the trigger into the training dataset to get the distilled dataset in the next loop. Finally, we can get our backdoor distilled dataset for the downstream model. Following this workflow, we indeed improve the backdoor attacks, and I will show the results later. However, many people will ask a question: why do you need to update the trigger at each epoch, which is duplicate for the final result? It's true that the trigger in the beginning is different from the last, but only update the trigger in the beginning is same as naive attack. If the distillation epoch increases, the trigger will be treated as a noise. In addition, if we only update trigger in the last several epochs, for the distillation dataset, sometimes it will not compress the trigger information into the distilled dataset, which will make the learning cost much higher. Thus, we choose to optimize the trigger at each epoch during the distillation process. And we also find another interesting phenomenon, which I will introduce it later. Here are the experimental settings. I list two different dataset techniques here. The first one is dataset distillation, which is the fundamental work of the entire dataset distillation family. To distinguish with the dataset distillation technique, we use DD to stand for this paper. And the second one is dataset condensation with gradient matching, and the short name is DC. And we choose two different upstream models, which are commonly used in dataset distillation works: AlexNet and convolutional net. Note that calculating the gradient of original training dataset from batch norm layer in the training mode in the dataset distillation is wrong. So ResNet or VGG cannot be used in these models, in these algorithms. For the evaluation metrics, we choose attack success rate to measure the attack performance and clean test accuracy to measure the model utility. I also list some images here. For distilled images, they can perfectly hide the trigger information in the bottom right corner, and they are totally different with the original training dataset. And here are the experimental results of ASR and CTA. Clean model in blue bar means that the dataset distillation process uses clean model, clean original training dataset, and tested by the clean test accuracy, dataset for the model utility, and naive attacks poison test dataset for the attack performance. So from this figure, most of the DOORPING are close to 1.0 of ASR, which is much better than the clean model and naive attack. For the model utility, comparing with clean model, DOORPING and naive attack have no clear utility degradation. And we also conduct 12 different ablation studies in this work. And due to the time limitation, I will not introduce them all. So I select some interesting findings here. If you have interest about the others, you can read our paper. For most common studies like poisoning ratio, trigger size, and distilled epochs, the results are similar to the other backdoor attack works. So first, somebody will ask if this method can be transferred to some complex dataset, because most dataset distillation don't have a good performance on that. And here we use CIVAR10 as our test. Although the model utility is not as good as the original ones, the DOORPING can perfectly extend to this dataset. I believe with dataset distillation technique improving, utility is not the problem we need to concern, but backdoor attacks are still the one we need to address. So in default setting of the dataset distillation work, the downstream model is the same as the upstream model. Thus, we would like to know if we can use different downstream model for the test. So we choose two model architectures, AlexNet, ConvolutionNet, and VGG11. We use AlexNet or ConvolutionNet as the distillation model, and the other two architectures for the evaluation. And here are the results. We only list the results for the CIFAR10 since the others are similar. From this table, we can know for DD algorithm, it has a bad transferability to other models. All the different downstream models have a clear utility degradation or ASR degradation. But for DC algorithm, we find that it can successfully transfer to other model architectures for many cases. And by analyzing the reasons behind it, we find that DD is the method that compresses the gradient of the original training dataset into every synthetic data, which means it's more related to the model architecture. But for DC, it matches the gradient of two datasets, which makes the distilled images more general and independent to the model architecture. The last study here is trigger trajectory. Recall that we update the trigger at each epoch. Theoretically, this trigger should be different. Therefore, we collect all the triggers and test them in the downstream model after the distillation process. So we find a very interesting phenomenon. The attack performance from this trigger can also achieve similar results as distillation phase. The trigger, for example, the trigger in the 10th epoch can achieve 1.0 ASR. And it will also achieve 1.0 ASR for the model trained by the final distilled dataset. So this is a unique feature offered by DOORPING. It enables the attacker to record a set of triggers that can later be used to attack downstream models, which make defenses such as the trigger autoencoder much harder. We also test 9 different defenses from 3 different categories. So we can see from the table, only strip has a good detection performance. A spectre can partly detect our attack, which is not robust. And the rest are not reliable defenses. We also analyze strip. We find that there is an obvious trade-off between the detection and the ASR. So from 0.6 to 0.8 of the ASR score, the performance of detection significantly sinks. So the trigger trajectory allowed the adversary to choose a suboptimal triggers to evade the strip detection. And that's all for my presentation. Thank you. I'm happy to take any questions.
Thanks, Yugen. Any questions? Please raise your hand and I will hand over.
Thank you for this presentation. It's a very nice presentation, but I have a small question. Did you try to use the same techniques for other types of data? Maybe some textual data, sequential data, for example? Because based on what I saw, that it's only focused on image data.
Yeah, that's right. We only focus on the image domain here, and we also write in our paper. But there will be some dataset distillation technique for the text dataset. But I think we will take text in the future.
One question also, may I know what kind of challenges will you face if you move to other type of data?
Because for the text dataset, you need to if you want to optimize the trigger, you need to update the trigger just based on the model architecture. So for the text data set, if you want to input this data set as similar to the images, we first need to convert into the embedded architectures. So that means in this phase, we need to think about how to inject the trigger and how to change the trigger back to the text. That's the, I think, it's a challenge for
Thanks for the presentation. Just a quick question on the motivation, because I think you do have a requirement that sets to the trigger, the original trigger for the distillation, right?
Yeah.
So if you already have the original trigger, you probably can get the natural trigger. So you no longer needed the and I do think the natural trigger can still have achieve a high ASR in the downstream. So why you still need to make a putative trigger in here?
So that's an interesting question. So for the natural trigger, I think if we just test, we don't need to optimize this kind of triggers. I think it's quite similar to our naive attack. So that means if we add a trigger into the training dataset and use it to distill the synthetic dataset, maybe this trigger will be treated as the noise for distillation process, because we need to comprise the information, a lot of the information from the training dataset into some small synthetic data. So that's why we need to update the trigger. So if you want to use the natural trigger for the updation, I think it's quite similar to the random initialize as our attack, as our method.
Other questions? I have a kind of a naive question. So for the trigger, are these triggers kind of work in a deterministic way or probabilistically, meaning that will the trigger always succeed or it succeed with a certain probability?
For the downstream model and the distillation process, there will be a lot of triggers for us. For example, we have 400 triggers because we have 400 elements of training. So these triggers, sometimes it can work, but mostly it can work because we optimize it. But sometimes it will fail. Yeah.
Thank you. Any other questions? If not, let's thank you one more time.